In this question, we need a data booklet. The question is an example of a diprotic acid. It is a cis-butene dioic acid. Like diprotic acid means it can donate 2 protons. Okay. Which indicator would be the most suitable for measuring the endpoint at a neutralization of a proton at which the pKa is 6.33? So pKa is 6.33, which is the most suitable one? We have ceresol green is there, bromothymol blue is there, litmus is there, and phenolphthalein. Which position? So the indicator will show a color change when pKa is equals to pH. Okay, that is usually what happens when pKa is equals to pH. The indicator show a color change. pKa you can say
like the pKa is 6.3.
So pH 6.3. So we'll check which indicator is more suitable in this range. Okay. Like here, this is the answer key. The ranges are given here. Reduction indicator. Here I miss indicator. 19. Yeah, this is page 19. Now, in this case, we have the graph, we have 2 regions are there. This is for the first color change, and mainly we are looking for the indicator which will work, because the best indicator is the one which show a color change in this region. Okay, like the vertical region, that is our best indicator. Even if it is, the graph was like this, 6.3 pKa means 6.3 means we want it to have a color change around 6.3, but according to the vertical range, if the graph was like this, and when I select an indicator, Alhamdulillah, when I select an indicator, I will select for vertical region. That is the best indicator. Like we always look for the indicator which show a color change in this vertical part. Okay. Now, when you see this graph, this is the first color, this is the first part, like 1 proton is being lost, and this is the second proton is lost. So what I will look for, I will look for the indicator which can show color change in this part. So what it is almost starting, it is like around 8 to 10, the vertical region. So I will look for the indicator which can show a color change from 8 to 10, the vertical section. So when we check bromoceresol green, so if we have, where is it? No, 2 vertical are there, but we want, look, if there is a color change in a first vertical region, then how I will know that the reaction is complete? I will, because what happened when acid, it's a diprotic acid. Diprotic acid means it can donate 2 proton. Let's say an acid was like H2A, and it was reacting with the sodium hydroxide. So first it loses 1 proton, so it will become HA minus, and then there's a second reaction happen. It loses another one. I want the color change when completely acid is reacting. If I select an indicator for this range, then it won't be suitable. Why? Because when the indicators show a color change, only one proton is lost. I want the acid to react completely. I want it to lose completely, so it will react. Like I will identify how many more, what volume of acid is completely reacting with an alkane. Yeah, if there was third one, I'll check with the third one. But usually it does not happen. Usually diprotic is a very common.
Like to check.
Like how much total acid is completely reacted, not about the partial. Because when there's a first color change, still only one proton is lost from that acid.
Yeah.
When there's a second color change, two protons are lost from that acid.
Yeah.
And we want, when second proton is lost, what is the color change? So we can identify that acid is completely neutralized by an alkane. So we always look for a vertical part. So if you have a bromocerol green, it's showing a color change, but from 3.8 to 5.4. So it's not suitable. Next we have bromothiamol blue. Bromothiamol blue is, there is bromothiamol, yeah, here. Bromothiamol blue, it shows a color change from 6 to 7.6. So not in the range, because our range, vertical range is from 8 to 10. If I check litmus, litmus is not at all suitable indicator because it has one color in acidic, one color in alkaline. It does not show any specific transition of the color. And the last one is the phenolphthalein. So if you have a phenolphthalein, you can see changing from 8.2 to 10. Exact color change will be at 9.3, but can show a transition of the color from 8.2 to 10. So it means suitable will be phenolphthalein.
Okay.
Clear?
Yeah.
Colorless in acidic and alkaline, it is red or pink. Is it clear?
Yeah.
So always check for the vertical range of the graph.
The last one, like we check for the last one, I mean, the reason of the says we do not want to check, like, we only check the volume when the acid is completely like reactive.
Yeah, this is a part where acid is completely reacted with an alkali. So we want the end point in this region. That's why we selected this range.
Will they sometimes like ask to check for the partial or like they won't mention any?
No. Full. You always check for full.
Always.
Next is at 25, the pH of a water is 7. At 100, the pH of a water is 6.4. What can we deduce? Look, when we increase the temperature, the water, what are the dissociation of the water? The water molecule dissociate into H plus and OH minus. This is a dissociation of the water. Okay. The water molecule dissociate into H plus and OH minus. It's a dissociation. The forward reaction is endothermic. And remember, the product of H and OH, when we increase the temperature, this product will increase. At 25, it is 1 into 10 to the power minus 4.
Yeah.
At high temperature, we'll get more H and more OH. So the concentration of H and OH will increase. So this product will also increase. And if the product will increase, what will happen to the pH? The pH will decrease. And what will happen to pH? pOH will also decrease. And the range of a scale will also decrease. Like at 25 degrees centigrade, when you add the pH and the pOH, the sum of a pH and pOH is equals to 14. But at higher temperature, when you add the pH and the pOH, the sum will not be equals to 14, the sum might be 13. Because more hydrogen and hydroxide ion, so the pH of a solution is pH and pOH both are decreasing. When the decreases, so the sum will also decrease and the solution will be neutral at 6.5. This solution will be neutral at 6.5. Why? Because when the pH is 6.5, The pOH is also 6.5, so the total will be 13. Here, when the pH is 7, pOH is also 7, so the total will be 14. So the solution at 25 degrees centigrade, the solution will be neutral at 7 pH, but at higher, like example, let's say at 50, the pH of a solution will be 6.5. pOH is also 6.5, so solution is also neutral because the pH and pOH is same.
Yeah, and like is the total the pH is like 6.5 due decrease in pH and pH.
Yeah, and because see, pH is equals to minus log of hydrogen ion concentration.
But at 25 it's 14, right?
Yeah, at 25 it is 14. And pOH is equals to minus log of OH ion concentration. When the amount of hydrogen ion or hydroxide ion increase, the pH and the pOH will decrease.
Yeah.
And the pH, the product of a hydrogen ion concentration and the hydroxide concentration is equals to 1 into 10 to the power minus 14. When we increase the temperature, so the product will increase. There will be more hydrogen ion, more hydroxide ion. If the product will increase, so the value of the pH will decrease and the value of the pOH will also decrease. So the pH will decrease, pOH will also decrease. So what will be the sum? The sum will be less than 40. So the question is, what is the enthalpy change of dissociation of a water? Endothermic or exothermic? Endo. And the concentration of hydrogen ion higher at 100, yes, it will be higher because if the pH is lower, the concentration should be higher. So A will be the right answer.
So the dissociation is endothermic. I mean, because water won't dissociate unless we supply
energy. The bond will break.
But there are other dissociations which are exothermic, right?
No, dissociation, all kind of dissociation, thermal decomposition, they are all exothermic. Endothermic, I mean. When something break, bond breaking, because in a dissociation, bond only break, no new bonds form. So any kind of dissociation or decomposition is endothermic. Anti-inflammatory drug, ketoprofen, is shown. What is the molecular formula of this drug? How many? Yeah, how many carbon atoms are there? All are like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 are there. Then the only distinguished is a hydrogen. I have to count hydrogen. 1. This will not have hydrogen. This will have 1 hydrogen. This will have 3 hydrogen. This will not have any hydrogen. This will have 1 hydrogen. This will not have any hydrogen. This will have 1 hydrogen. 1 hydrogen, 1 hydrogen. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So total 14 hydrogen. So C16, H14, O3.
So we can also like CHO or H, but like decreasing the number of the from one from the one and one from the H.
Where?
With that bigger, like CHO or H, like to just represent that there is an OH group there.
But this is the carboxylic acid and a ketone. 2 groups are there.
Yeah, I said CHO, OH, but like subsequently decreasing the number from the group. Will that bigger as a form?
Yeah, it will be. Yeah.
Okay.
Then methanol has a number of medical uses. It can be extracted from peppermint plant. The structure is shown. How many chiral centers are there in one molecule? This to be a chiral center, 4 different groups should be attached to a carbon. This is not a chiral center, so 1, 2. This cannot be a chiral center. This cannot be a chiral center. This cannot be a chiral center. No, this can be. This can be because hydrogen is there This group is there. This side is this group, other side is this. And this one can also be a chiral center. Yeah, hydrogen is there. This one cannot be chiral because same. Hydrogen is there, but light and left are same. So how many chiral? Two chiral centers. Question 8. 3 chiral center. Huh? Where's the third one? How I missed the third one? This is one chiral center. One, two. This is not a chiral. This will also be a chiral. Why? Because CH3 is there. This group is attached. This group is attached. Like
CH3, not attached.
no, this is C. H. This will have. This is CH3.
How do you know that there's CH3 out there?
Because this is a line for carbon. This is a carbon. So this carbon will have a hydrogen.
I mean, there is.
This will have a hydrogen. This will have one hydrogen. This will have one hydrogen. This will have 2 hydrogens. This will have 2. So when you check, so this is one side, second, and hydrogen is there, and so this is a chiral carbon. This is also chiral carbon. This is also chiral carbon.
See the line on the.
Huh?
I couldn't see the outline. I thought you just draw the outline. You know, see,
Oh yeah.
That means that there are
3 chiral carbons. 8 isomers. Yeah. Question 9 and 10. Which of these reactions does not result in a formation of a racemic mixture? If a butene plus HCl. So butene is CH3, CH, double bond CH, and then CH3. And when it reacts with HCl, addition reaction will happen or occur. One side hydrogen will be added and another side Cl will be added. So this will form a.
That's a secondary answer.
What?
That's a secondary addition.
Yes, like what will happen? This is C1, like means first thing what we will do, we will check the chiral carbon is there. Because which of these does not result in a formation of a racemic mixture?
So it's one.
First, to understand the racemic mixture, we have to say like what is the like whether there's a chiral carbon or not.
Yeah.
If there's no, this has a chiral carbon.
Yes.
Okay, and both ways, like it might be chlorine bonded here, but it's not about the link. If but1ene, like I think the 9 is, yeah, because of equal amount is there, like this one is not forming a chiral carbon. Why it's not forming a chiral carbon? Because if it is a but2ene, and HCl is added, the double bond will break. One side hydrogen will be added, one side chlorine will be added. Okay.
Yeah.
So again, same possibility, like this might be might rotate a light clockwise or anti-clockwise. Both in addition reaction, both possibilities are there. But when we have clear, no.
The structure that you through
but2ene. But1ene, I mean.
is that a CL?
No, first a but1ene I drew, and it added HCl.
Yeah.
So when we add HCl is added, one side H will be there, another side Cl will be there.
Okay.
So as a result, this Cl is having both possibility, like any of the product it can form a racemic mixture. Because like it can attack from any side. The carbon cation, when this reaction, look, when this reaction will happen or occur, you have but2ene. First one.
Yes.
First, in electrophilic addition reaction, H plus will attack.
Yeah.
Okay, means it will form a bond with any of the Cl, any of the carbon. So let's say it form a bond with here, this one. Now this is a carbon cation. This carbon cation is which carbon cation? It is a tertiary, it is a trigonal planar. Why it's a trigonal planar? Like hydrogen is here, then CH3 is here, and then CH2 and CH3 is here. So because this has a 3 bonds, so if 3 bonds are there, means it will be a trigonal planar. So if it's a trigonal planar, as a result, what will happen? The Cl can attack, because when we have a trigonal planar molecule, the chlorine can attack from the right hand side or it can attack from the left hand side for addition. Same thing happens with butanene as well. So when it is butanene, like CH2 is there, double bond CH, then we have CH2 and CH3. HCl will break, hydrogen will form a bond, let's say hydrogen form a bond here. So this will be a carbon cation. This carbon cation is having, this carbon cation is, it's again a tertiary, like trigonal. Hydrogen is one side, another side is CH2, CH3, another side is CH3. So the Cl can attack from the left, Cl can attack from the right. So it can form a racemic mixture. No, this is not SN2. SN2 is when this is addition reaction. SN2 is a substitution reaction. When OH
can be like in case of like let's say with HCl, D and C. Okay.
But the thing is, if you see propanol, this is propanol. First, the double bond will break, H will be here. Then the CN will attack. So it can attack from any side. It can attack from the left. It can attack from the right. Okay.
Yeah.
I think C is there. D. Chiral enantiomer. Propanol. Okay. I do propanol. I do this one, propanol. When I do propanol, is this a chiral carbon? No. So if it's not a chiral carbon, means how it will be a racemic mixture.
Okay.
Like if you see propanol,
So there's a
CH3, C double bonded with O and H is there. Okay. When HCN is added, this H will be, the double bond will break, H will be added here. Then this CN can attack from right, can attack from left, and it will have a chiral carbon, like CH3 will be there, OH is there, H is there, and CN is there. So this is a chiral carbon. 2 minutes. So that's why D should be the right answer for this.